So we're going to start section 2.3. We won't finish it, but we're going to give it a start here today. Rates of change, and we're going to talk about notation and interpretation. Now, I mentioned in the last section in 2.2 that this phrase, instantaneous rate of change, also meant the slope of a curve at a point. And I said these are sort of interchangeable phrases. And I also kind of mentioned that there's a lot more interchangeable phrases than just those two. So let's actually put those first two down. So the first one, whoops, let me get my white one back up. The first one was the instantaneous rate of change. I'm going to abbreviate. You feel free to do so if you'd like. Instantaneous rate of change. And the other one we saw in the last section was the slope of a curve at a point. So those are the two that we've already seen. We talked about the third one. We didn't write it down. We talked about this also being the slope of the tangent line. I mean, not only did we talk about it, but we did some examples where we used that idea. The slope of the tangent line is the same thing as the instantaneous rate of change or the slope of the curve at the point. But there's two more that we haven't talked about. Number 4 is the limit of the slopes of secant lines. I'll draw you a picture about that one in a minute. And the last one that we will use most frequently, and if you've taken any calculus course before, the one you're most familiar with, is derivative. Let me draw you the limit of the slopes of the secant lines, and we'll just use a generic curve. So you can just draw this sort of over to the side. I have space more on the bottom corner than mine, but let's say we had this curve right here, and we're trying to find the slope right here. Oh man, that's huge. I need a smaller marker point. How about there? Okay, so we all know, because we drew them last time, how to draw that tangent line, right? So what we didn't really talk about is what secant lines looked like on a curve. So let's actually look at that really quick. If I were to do a secant line and I used these 2 points, say, then a secant line would look something like this. It just connects 2 points in the curve. But I'm going to take that yellow point and I'm going to make it get just, a little bit closer to the red point. And I'm going to draw that secant line instead. And I'm just going to let that yellow point get a little closer and draw that new secant line instead. And if I continue this process sort of indefinitely, indefinite processes are limits, right? We've done that in chapter 1. This little yellow point that's getting really, really close to the red point eventually becomes indiscernible, right? They become almost practically the same. And when that happens, as that limiting process is happening, those slopes of those secant lines is approaching the slope of the tangent line, which is exactly the slope of the curve at the point, or the instantaneous rate of change, or now, our newest one, the derivative. So that's visually what's happening to these secant lines that are getting really close to this tangent line. Okay. I already wrote them down. I didn't mean to have them here. There we go. Notation. So there are several notations then for derivatives. There's one that we're going to use the most frequently, but there's a couple others that come into play at different points, and it's really useful when they do come into play that they do. So first we have our function f of x. Okay, so we've got our function f of x, and we want to know notationally. Well, in the last section we talked about, these are just slopes, and slope I know how to calculate. It's change in y over change in x, right? Agreed? Right? This is slope, and it's change in y over change in x. That's a notation that we think about. So one of the ways that we could actually write down the notation is with the letter df over dx. D is kind of like meaning difference. The difference in f, the f values, those are my y values, the function values, divided by the difference in the x values, df dx. And that's how we read this. We read this as df dx, just the letters exactly like that. So I'm not going to say df over dx, it's just df dx. That's actually a really helpful notation because it has this sort of connotation of slope, which is exactly what we're calculating. When we calculate these things, we're calculating a slope, and it's a good reminder. The notation that we will use the most frequently because it so resembles our function notation is the one I introduced in the last lesson, f prime of x. And we will read it just like this, f prime of x. Again, it just means slope of the tangent line. The last one, my least favorite, but when it comes up, I just need to make sure you know what it is asking you. Looks like this. And we read it like this. We say d dx of f of x. d dx of f of x. All it's just saying is the change in x, the d dx is the change in the x, right, of the function f of x, how it's changing. Just another notation. It is the one we use the least frequently. Some other language you'll sometimes hear said when you're talking about any of these. There's a couple other phrases just to be aware of. The rate of change of f with respect to x. Rate of change of f with respect to x. Or the one we probably will use the most frequently, the derivative of f with respect to x. And let me leave you with one final thought. Some of you are sitting here maybe thinking like, why do we keep saying with respect to x? And there's a really good reason for it. It just doesn't feel like it right now. The reason we say with respect to x is because you are going to be working on calculus with only one variable in it, x. But there are other calculuses, multivariable calculuses, where you have more than one variable. Obviously, if you had more than one variable, it would matter what the variable is that you're considering taking the derivative with respect to. So that's why that language is embedded in there, is because it allows us to broaden our description if you continued on into higher pieces of calculus with more than one variable. So just letting you know that's why it's there. We won't be doing that, but that's why that language is there. All right, we will not be doing homework on this section yet. We will finish it next time, and we will do homework after that. So have a great couple days, and I'll see you guys on Thursday.